having discussed some of your initial questions on the topic, let's get into the mechanistic pathways. Okay, now there are four variables you need to consider, and they are listed in the order of importance. The first one is the substrate, the second is the nucleophile, third is the solvent, fourth is the temperature. So as you're given a chemical reaction, do not look at the reagents, go look at the molecule itself that contains the leaving group and focus specifically on the carbon containing the leaving group. Based on that knowledge, you can go further in determining what will be the mechanism. So before we get on to that, I have come up with this schematic which kind of summarizes everything we've learned up until this point, just to get you to remember what it is that you're actually doing. So you have a substrate, it contains a carbon, and the carbon contains the leaving group. In comes the nucleophile, attacks the leaving group and displaces it. Now keep in mind, all reactions E2, E1, Sn1, Sn2 are carried in a solvent medium at certain temperature. It could be ambient, or it could be moderate, or it could be high temperatures. None of these reactions are gas phase, so they are carried out in a liquid medium. So if the nucleophile completely replaces the leaving group, then it leads to the formation of a Sn1 or Sn2 product, but we don't know which one easily, right? That's what we're trying to figure it out. Similarly, if the leaving group is completely gone and is not replaced by the nucleophile, instead we have a double bond formation, then that leads to an E1 or an E2. That kind of captures everything and put it in a picture format to us. So now if you see, those variables are sort of, in your vision, right? You can see all the four variables described in the picture. So let's look at the first substrate. Based on the formative assessment data that we collected from the 10 questions, I can tell that most of you have no problem determining what type of carbon substrate do you have. That seems to be of no issue to most of you. So based on that, there are two concepts to consider. One is steric hindrance and the other is the carbocation stability, and they are entirely related to the nature of the carbon in the substrate itself. So if your carbon is primary that contains the leaving group, then there's a good chance your mechanism would be Sn2, because it's the least sterically hindered, right? You have a carbon containing the leaving group surrounded by two hydrogens compared to a tertiary that's containing a lot of bulkier groups. So typically primary carbons substrate 99.9% of the time go through Sn2. And that's the order: primary greater than secondary greater than tertiary. Carbocation stability is exactly the opposite of steric hindrance. In other words, you want more steric hindrance for carbocation stability to increase. So the order is going to be reversed, but there's a catch. You can have Sn1 or E1. So if you have a tertiary carbon that contains the leaving group, it's not going to be Sn2 for sure. It will be either Sn1 or E1. Okay. Now we only looked at the extreme. I mean, even though we say secondary is better than primary in the carbocation and secondary is better than tertiary in the steric hindrance, secondary is kind of a sensitive carbon. It can switch gears differently. So we'll focus it differently as we get to other variables. Okay. Based on substrate alone, secondary carbon can undergo Sn2, Sn1, or E1. Do you see? Do you see? Yes, secondary carbon is sort of in the midst of things. So if you have a secondary carbon, you have to use other variables to determine where things might go. But based on the extremes, the carbon substrate alone can kind of conclusively tell you where you're going. So let's get into nucleic. I'm going to go through all of this information in here. Well, I do not want you to memorize. You've seen it before, okay? If you have any of the negatively charged species, there's a good chance they are strong bases. For the most part, they're strong bases, okay? Now, you also have alkoxides, which is the RO minus, means it's an oxide, right? If your oxide is either O minus or sometimes it's shown with the sodium or potassium version of it. They both mean the same. So if you have an oxide, that is a strong base as well. But if your oxide is really big, then that's a bulky base, which I have indicated by the red box. The only reason I have the purple box is just to tell you the CH3O minus Na is same as the CH3O minus. They're the same. It's just the sodium is shown in one, sodium is not shown in the other, simply because some of you might be intending to go on to take MCAT exams. On some MCAT questions, they show the oxide with the sodium. In some cases, they don't show the oxide without the sodium, but they both mean the same. That's why I've shown both versions in the purple box. So don't try to memorize all of this. Similarly, weak bases are typically weak or neutral bases are typically don't have a charge. And of course, the bulky is the same. The only difference is in the oxide that are bulky strong bases, you either have a sodium or just the negative. Whereas in a bulky weak base, you have the negative replaced by a hydrogen. Okay. Now, say you have a tertiary substrate. Okay. And we know tertiary substrates can have Sn1 or E1, right? But when you have a tertiary substrate, but you have a really strong bulky base, then you have an E2. Your tertiary carbon substrate can only lead to an E1 if it's a weak bulky base. Okay, we said earlier, based on carbocation stability, tertiary carbon containing the leaving group will lead to an Sn1 or E1. But it's only E1 if it is a weak bulky base. But you start with a tertiary carbon, but you're also starting with a really strong bulky nucleophile, and then it leads to an E2. Okay, I think as we conclude this discussion and show you the flow chart, it'll become much more easier. The solvents. Now, there's only two types of solvents. There's the protic and aprotic. Protic means they're generally water soluble, or they tend to make hydrogen bonds. Aprotic means they're not water soluble, so the reagents that you use must be able to be dissolved in the ones you shown here. So typically they have letters. DMSO means dimethyl sulfoxide, DMF, and things like that. Okay, aprotic solvents typically favor Sn2. Protic solvents with a strong nucleophile favor E2. Okay, and with Sn1 and E1, it's always almost protic solvents. Okay, so when it comes to either Sn2 or E2, if you're shuffling, you look at the solvent. If the solvent's aprotic, then you know it's Sn2. If the solvent's polar protic, but you still have a strong nucleophile, then you have a E2. Because with Sn1 and E1, it always happens with a protic solvent and a weak nucleophile. Strong nucleophiles only favor Sn2 and E2. But between the strong nucleophile, say you have just strong, not bulky, but a strong nucleophile, then you look at the solvent. If it's a protic solvent, then it's a E2. If it's an aprotic solvent, it's an Sn2. Okay? Polar protic solvents with the weak nucleophile generally, and a tertiary, usually favors Sn1 or E1. I just explained that before I put that up there. Okay? Temperature. Higher temperatures are necessary for elimination reactions. Okay, say you have a higher temperature primary substrate, strong and or bulky, doesn't matter. If you have a primary carbon substrate, generally Sn2 is favored, but to prevent Sn2 from happening, you can throw the high temperature, and then you can have a strong nucleophile or a strong and a bulky nucleophile, then it favors E2. Okay, high temperature tertiary substrate, period, it's going to be E1. Whether it's weak or weak and bulky, it doesn't matter. So high temperature, the carbon substrate doesn't even matter. If it is strong or strong and bulky, then it's E2. High temperature carbon substrate is tertiary. Weak or bulky, weak, it's E1. Okay, and I've just shown you all the leaving groups. You do not have to memorize this. Now let's look at the flow chart. Okay, this is where we kind of summarize everything we've learned. So nature of the substrate. First, you go to the carbon containing the leaving group and you determine, just literally write down, is it primary, secondary, or tertiary. Say you determine it's primary. Yes, it's primary. Does your reagent is a strong bulky nucleophile that's an oxide? Remember that I showed you the oxide in the red box? If it looks something like that, you ask the question, is it a strong bulky nucleophile? Yes. Then, like I shown you earlier, primary carbon substrate with a strong bulky nucleophile, it's period E2. Say you determine you know, then you ask the question, is it a strong nucleophile? If you determine it is one of those negatively charged bases, then it's a strong nucleophile. And you say yes, then you ask the question, because remember there's also solvent. Is the solvent polar protic? If the answer is no, because remember, polar protic, it's no, then you have Sn2. If it's S, it goes back to E2. Does that make sense? It's taken a lot of work to get this flowchart organized as it looks like now, because this is very key. Say you determine the carbon substrate containing the leaving group is tertiary, yes. Then you ask the question, is the nucleophile strong and bulky? Again, if you say yes, then you have an E2. Strong means it's generally E2 or Sn2, okay? But if it's bulky, it's E2. And you say no, then you ask the question, is it a weak bulky nucleophile? If you say yes, and then you look at the temperature. If you say yes to that as well, then that's an E1. If you say no to the weak bulky nucleophile, then it is just a weak nucleophile. And if you say yeah, if it is no, but then you have an Sn1, right? And then you say no to the high temperature as well, then that also leads to an Sn1. Say you determine your carbon containing the leaving group to be secondary. Yes, it is secondary. Then you again ask the question, is this the strong bulky nucleophile? If you say yes, then it is an E2. If you notice, after you get the initial yes, you're always asking the first question, is it a strong and bulky nucleophile? Which also follows the sequence that we have the substrate, then the nucleophile. Then only we ask the question about the solvent. Say if you say no, it's not strong, then you ask the question, is it a strong nucleophile? And if you say yes to that, then again you ask the question, is it a polar protic solvent? Again, if you say yes, then you go to an E2. If it's say no, it's an Sn2. Does that make sense? Like how it's all so related and beautifully structured, and there's no magic or rocket science behind it. It is simple, straightforward science. Okay, so you always look at the substrate, then the nucleophile, then you look at the solvent and temperature. Temperature really is not that big of a deal. If your nucleophile is strong and bulky, then we don't really focus on temperature at all. That's why you see temperature is only appearing in one area of the flowchart. Mostly it's either substrate or nucleophile or solvent. All right. Now I can keep on refreshing this flowchart like 1,000 times, but the idea is pretty simple. Okay. If you look at it more than once, you clearly get the idea there's a recurring pattern. Let's look at 2 or 3 examples, and I'll leave you with a few examples just to apply the flowchart. Okay. So here's the example. What's the first thing you look at? You look at the carbon containing the leaving group. That's a substrate. The carbon containing the leaving group has got 2 hydrogens, so it's primary. So we know right away it had to be Sn2 or maybe E2 if it's a strong bulky nucleophile. Then we go to the nucleophile. OH minus is just a strong nucleophile. It's not a strong bulky nucleophile. Right away we know it's an Sn2. And it makes sense. The solvent is also aprotic. There we go. Just replace the Br with the OH. And I have these 2 questions to write. What is the rate of the reaction? Well, we determine first is Sn2, right? Sn2 is a bimolecular reaction, means it depends on the concentration of both the nucleophile and the substrate, right? So we write the rate law to be this. And what is the product of the reaction? All we do is simply replace the Br with the OH. There we go. See just how I simply applied this? Question 2. All right, again, as we start always with the carbon containing the leaving group, and that's the substrate, right? So it's a secondary. So, well, secondary is a little here and go type thing. So we look at the nucleophile. The nucleophile is strong, right? Now keep in mind, when we looked at secondary, we asked the question, is it a strong bulky nucleophile? If it is yes, then it's E2. If it's no, then we go to the solvent, and if the solvent is polar protic, then we get E2. If it's aprotic, then we get Sn1, right? And the solvent is aprotic, so it is again an Sn2, right? So because it's a secondary, we can have an inversion in configuration. So inversion is, if you have a open wedge, the product should be closed wedge. I'm also asking for the rate. Again, Sn2 is bimolecular, so we have, this is the rate law, and here is the product. See, it's, oh yeah, Cl is replaced by Cn. There we go. That's question 2. Question 3. Okay, I'm going to just put it all up and explain it. Okay, so here we have a tertiary substrate containing the leaving group. So tertiary, well, again we ask the question, is the nucleophile strong and bulky? Well, the answer is no, so it can be E2. It had to be Sn1 or E1. Then we go ask if is the nucleophile weak and bulky. We still come out as no, because NH3 is weak. It's not weak and bulky. And is the solvent protic? Yes, it is, but it doesn't matter for Sn1 and E1. So it can only be Sn1, right? Really. And Sn1 leads to racemic mixture. I've only shown one of it. You can also have plus the broken wedge as well. So that's Sn1. And I've only shown, remember, Sn1 reactions are unimolecular. That means it only depends on the concentration of the substrate and not the nucleophile. So that's the rate law. Does it lead to inversion or racemic mixture? It leads to a racemic mixture. I've only shown, like I said, the closed wedge product. You can also have plus the open wedge product. Okay, and that's Sn1. And finally, I have one more practice problem. So again, you go to the carbon substrate. We establish it's a primary substrate. So then we look at the question and ask, is it a strong bulky nucleophile? And the answer is yes. Right away, primary substrate, strong nucleophile. You don't need to even look further. It's going to be an E2. But all other things also check out. It's a polar protic solvent, and it's also got high temperature in it. While temperature is not necessarily a requisite here, that also fills the block. So what's the rate of the reaction? Well, first you have to determine the reaction, and we establish is E2, and E2 is also bimolecular, so the rate depends on the concentration of the substrate and the nucleophile. And then the product is a formation of a double bond. Okay, and that's sort of what is the application of the concept. Now I have given you additional practice problems here. Go ahead and try them out and let me know what you come up with the next class. All right, and we'll further dwell a little more on this topic, get you comfortable with it, help you understand the topic better, and then eventually we will have another formative assessment on the entire topic to summarize everything. All right, so just keep working at it and let me know if you have any questions. I'll see you next class.